Welcome, everyone. I'm excited to kick off today's presentation. We'll be exploring an important topic in wastewater treatment. What is sludge bulking? In this session, we'll look at how sludge bulking impacts treatment plants, why it happens, and what it means for maintaining clean and efficient water systems. Over the next few slides, we'll cover the causes, effects, and potential solutions to this common challenge. So, let's dive in and understand why sludge bulking is such a critical issue for water professionals everywhere. Let's take a closer look at the basics of sludge bulking. Essentially, sludge bulking disrupts the activated sludge process by preventing proper settling in secondary clarifiers and sedimentation tanks. Under normal conditions, microorganisms form these compact clusters called flocks, which settle quickly and efficiently. But when bulking happens, these flocks lose their ability to compact properly, turning into a light, fluffy mass that resists settling. The main culprit behind most bulking incidents is the excessive growth of filamentous bacteria. These bacteria grow in long, thread-like strands that extend beyond the normal flock structure. Think of it like trying to compress a pile of cotton balls versus a pile of marbles. These tangled filaments physically prevent the sludge from packing densely enough to settle properly. And the consequences don't stop at poor settling. When sludge doesn't compact and separate as it should, it often carries over into the final effluent, increasing the amount of suspended solids in the discharged water. This can lead to regulatory violations, environmental concerns, and often requires additional treatment steps to meet discharge standards. So, understanding how filamentous bacteria cause these issues helps us better manage and prevent bulking, ensuring our treatment processes run smoothly and meet environmental regulations. Let's talk about why sludge bulking really matters in our treatment process. The key tool we use here is the Sludge Volume Index, or SVI. This measurement tells us how much space 1 gram of suspended solids takes up after 30 minutes of settling. Under normal, healthy conditions, the SVI should be between 50 and 150 milliliters per gram. This range indicates that our sludge is settling well and forming a compact mass, which is exactly what we want. Now, if the SVI goes over 150 ml per gram, that's a big red flag. It means the sludge is not settling properly and is occupying way more space than it should. When we see SVI values jumping to 300 ml per gram or even higher, it's a clear sign of severe bulking. This can be 2 or even 3 times the normal volume for the same amount of sludge, which can cause serious operational issues. Why does this matter? First, there's the regulatory risk. Excessive suspended solids in our effluent can lead to violations of discharge permits, which might result in fines or legal actions. Plus, regulatory agencies and the community are likely to scrutinize us more closely when things go wrong. Operationally, bulking can cause chaos. When sludge washout happens in our clarifiers, our biomass inventory drops, which reduces our treatment capacity. This forces us to constantly tweak processes, monitor more frequently, and sometimes even cut back on flow or implement emergency measures to keep things under control. Economically, the impact is just as significant. Bulking means handling more sludge, which drives up costs, more chemicals like polymers, more energy for pumping and aeration, and additional labor for monitoring and adjustments. Sometimes, we might need emergency chemical treatments, which only add to the expense. Imagine a real-world scenario, a plant operating normally with an SVI of 100. Suddenly, bulking occurs, and the SVI jumps to 300. That means the same mass of sludge is now taking up 3 times the space. It can overwhelm the clarifiers, reduce solids retention time, and lead to solids carryover. The ripple effects are felt everywhere, from process control and maintenance to regulatory reporting. That's why keeping an eye on SVI and preventing bulking is so crucial for smooth, compliant, and cost-effective plant operation. Let's now look into the causes of sludge bulking, which is essential for understanding how to prevent it. Bulking doesn't happen randomly. It results from specific biological and operational factors that create favorable conditions for problematic microorganisms. Essentially, It's about environmental conditions shifting the competitive balance among microbes in the activated sludge system. One of the main culprits is filamentous bulking. When dissolved oxygen levels drop below around 2 milligrams per liter, filamentous bacteria gain an advantage over the flock-forming bacteria we want to dominate. These filamentous organisms have adapted to thrive in low-oxygen microenvironments by extending their filaments to reach oxygen at the surface of the flocks. Poor aeration, high organic loads, or equipment failures often cause these low oxygen conditions. Another key factor is nutrient imbalances. The ideal nutrient ratio for flock-forming bacteria is roughly 100:5, 1 for carbon, nitrogen, and phosphorus. When nitrogen or phosphorus become deficient, filamentous bacteria, which need fewer nutrients, tend to flourish. Industrial wastewaters often lack these essential nutrients, creating the perfect environment for bulking. pH extremes also play a role. Most activated sludge systems perform best between pH 6.5 and 8.5. When conditions are too acidic, say below pH 6, it favors fungal filaments and certain bacteria that tolerate low pH better than our desired flock formers. Sudden pH changes can shock the system and trigger bulking episodes. Temperature is another factor to consider. Warmer temperatures between 25 and 30 degrees Celsius, or 77 to 86 Fahrenheit, tend to accelerate the growth of filamentous species. That's why during summer months, we often see increased bulking incidents as biological activity ramps up with the heat. Seasonal variations in temperature strongly correlate with bulking frequency. Now, not all bulking involves filamentous bacteria. There's also what we call non-filamentous bulking, which is caused by bacteria producing excessive extracellular polymeric substances, or EPS. This is essentially a sticky gel-like material that traps water and makes the sludge viscous and poorly settling, what we refer to as slime bulking. This usually happens when there are severe nutrient deficiencies or exposure to toxic compounds stressing the microbial population. Lastly, operational factors like variable influent characteristics, which stress the microorganisms, can favor opportunistic filaments. Low recycle rates, meaning inadequate return of settled sludge, reduce biomass concentration and cause feast-famine cycles that promote bulking. And hydraulic overload, when flow rates become too high, reduces the time available for proper settling and can wash out the slower-growing, desirable organisms. By understanding these causes, we can better tailor our operational strategies to prevent and control sludge bulking effectively. Controlling and preventing sludge bulking is all about taking a comprehensive approach. It's not just about reacting when problems occur, but actively preventing them through a combination of strategies. The key here is understanding that prevention is much easier and more cost-effective than trying to fix a severe bulking episode after it happens. So, proactive monitoring and maintaining optimal operating conditions really form the foundation of an effective bulking control program. Let's start with operational control strategies. Maintaining the right nutrient balance is crucial. We aim for a C/N ratio of about 100:5:1, which we can achieve through regular testing of influent characteristics and, if needed, adding nutrients carefully and precisely. Many facilities now use automated systems for this. Oxygen management is equally important. Keeping dissolved oxygen levels above 2 mg/L throughout the aeration basin is essential. Sometimes, installing additional aerators or optimizing diffuser placement can help. In some cases, zones with higher dew levels, above 3 mg/L, provide extra insurance against oxygen depletion in localized areas. Controlling the FM ratio, the food-to-microorganism ratio, is another critical factor. Lower ratios, around 0.2 to 0.4 pounds BOD per pound MLSS per day, tend to favor flock-forming bacteria over filamentous ones. We can adjust this by managing waste sludge rates and influent loading. Recycling activated sludge effectively also plays a role. Returning a higher percentage of sludge, say between 25 and 100% of influent flow, helps maintain enough biomass and reduces the conditions that promote filamentous growth. Fine-tuning these rates based on settling performance and MLSS targets is key. When it comes to intervention and treatment, chemical controls like chlorine, polymers, lime, and hydrogen peroxide can be used selectively to damage filaments or improve settling. Biological methods, such as bioaugmentation, selective wasting, and creating zones that favor flock formers or even introducing predatory organisms, are also valuable tools. Monitoring is critical. Daily microscopic examinations, tracking SVI trends, identifying and quantifying filaments, and real-time measurements of dew, pH, and nutrients all help us catch issues early. I'd like to highlight a success story from an industrial plant that was struggling with severe bulking, with SVI values exceeding 400 mLg by diagnosing the problem quickly, thanks to microscopic analysis, and implementing targeted phosphorus dosing along with better aeration control. They managed to turn things around in just 2 weeks. Their SVI dropped to 120 mLg, and they regained compliance. The bottom line is that fighting sludge bulking is an ongoing effort. It requires constant vigilance, good monitoring, and quick action at the first signs of trouble. Facilities that invest in comprehensive monitoring, keep equipment well maintained, and train their operators to recognize early indicators will experience fewer severe episodes and lower operating costs. Just like in medicine, prevention truly is the best cure. Staying ahead of the problem always pays off in the long run.